Hello everyone, this video is about to train machine learning models on retro games using OpenAI's Baselines and GYM Retro, and how to integrate a new game that is not yet supported in the GYM Retro GitHub repo. So more specifically, we're going to integrate a racing game called Hang On the Sega Master System and train a model to beat the entire game. So right now what you see is a CNN model trained for 500 million frames, which is enough to beat the entire first level of difficulty of a Hang On. If you want to skip to a specific section, I will put timestamps in the description down below. So for example, if you're already all set up and just want to know how to integrate a new game using OpenAI's integration tool, you can skip directly to that. Last point before we start, while it will be easier if you already have some basics in reinforcement learning, neural networks, and Python, I will do some very light introduction, enough so you can start training models and understand what's going on. So I've also put a timestamp for that. To expand a bit on that point, I find it easier to have a concrete example to play with and tweak first and learn the theory along the way by experimenting. For example, in this case, a game you like that you want to beat using ML, as opposed to learn a bunch of theory first without any specific goals. So it's important to have a project where you can directly test your knowledge and tweak along the way. I think it's much easier for learning. So we can start the setup. I recommend using a clean install of Ubuntu 18.04, and this guy will assume you have it. You can still use Ubuntu 20.04 or Windows 10, but the setup process is harder, and actually installing dual booting with Ubuntu 18.04 might save you lots of time. I have made a blog post a while ago on how to set up. You can follow it there if you prefer. I will put the link down below, but I'm still going to go over these steps in the video. Assuming you have a clean install of Ubuntu, we will need to install some packages. So sudo apt-get install. Probably need to get CMake, obviously Python 3. Git the zlib, the OpenAI lib, and ffmpeg. ffmpeg is because you most likely want to be able to render all your training in a video. Sometimes it's helpful to debug what happened and how the training involved. So you're gonna need to install that. I already installed it, so no need for me to install. Next is to install some Python packages. So scikit, OpenCV for Python. There's NERL, GYM Retro, and GYM because GYM Retro depends on GYM. So that should be okay. I installed it too, so I won't go through that. So next step is to install TensorFlow. Now you have two choices for TensorFlow: the CPU version or the GPU version. If you have an NVIDIA card with CUDA capability of 3.5 and up and 2 GB of VRAM, I recommend you install the GPU version. And I recommend you install CUDA 10. Well, actually, you must install CUDA 10 because the TensorFlow GPU 1.14 needs CUDA 10. And if you have an AMD card, you can check out ROCm. I made a video about how to install ROCm on my channel. Typically, only a subset of AMD cards are supported. For example, the RX 580 is no longer supported with the newer version of ROCm, but you can install older versions like 3.3. So you must check out the list first before installing ROCm, because it's a pretty long process. I'll put the link in the description down below so you can check that out. So in our case, we have a MX150. It's a Pascal-based GPU for laptops. We have 2 GB of RAM, of VRAM. So we can install TensorFlow 1.14, the GPU version. So if you only want to install the CPU version, you just need to type TensorFlow like that. Next, we need to clone the OpenAI GitHub repo, the baseline and retro. So you can go to their repo here. Type git clone this, and it's the same thing for retro. I already done it, so I won't do it again. That's it. But once you clone retro, you need to install it, because otherwise you will use the default one, Gym Retro, that you previously installed. So in my case, I install it here. So to install your version of Gym Retro, you do pip install, and we'll use the one you synced, because after that we're gonna add new games. You're gonna have to modify it, so it's better to modify one you clone rather than the default one. So with this, we'll install the current version. Next, before we start testing our setup, we need to import the ROMs. For obvious reasons, the ROM doesn't come with retro, so you need to get it elsewhere. In case the ROMs are in my downloads folder. So once you CD in your folder, you can use the retro module to import it, and for the current directory. So the numbers you see is the checksums, or the checksums. So how this works is that it copies the ROM and renames with the appropriate extensions to the relevant folder in retro. In this case, it copied the Super Mario Bros. NES ROM in its folder, and the way it does that is that every folder has a checksum, so that's how it knows which ROM goes where. And also that means that, so I think this is the American version, but if you have the Japanese version of Super Mario 1, the checksum obviously will be different, so you won't find it, you won't copy it. And also the tools might not work, because the values in RAM will be at different places probably. So be sure you have the right checksum. So if you see your ROM doesn't get imported, just check the checksum, and check also from which region it comes from. Now we're ready to test our setup. So we're gonna test with a game, classic game, Super Mario. So first you need to CD in your baseline directory that you previously cloned. So this parameter is for selecting which algorithms you're going to use. There's many ones like DQN, E2C, PPO2. Later in the video, I'm going to go a little bit over that. Next, you need to specify the environment. In our case, it's the Super Mario Bros. Environment. It's the name of the folder. So let's say you want to run on Contra, then you're going to use that name like Contra-NES. Which type of neural network you want to use. In our case, is the default one, the CNN. Actually, you don't need to write this this argument because you're going to use this by default, but just for clarity, we're going to specify it. Number of time steps for the training. We're going to try 10,000. 10,000 is not enough to learn anything really, but it's just a test to see if the setup works. And play. So that means play means after the training is finished, it's going to automatically open a window and run the trained neural net, so we can see the results. Another way of seeing the results is to save it to a video. That I'm going to show that later. So let's try that. While it runs, if you want to see the GPU usage in the loop, you can use this argument, the -L1. That means every second it updates. So you see it uses 800 megabytes of RAM. Depending on the model you use and the algorithm, it might be lower or higher. So as you can see, the training FPS was a bit over 400. That's what's expected for types of for GPU. And also we have our CPU is 4-core, 8 threads in this case. So that's a type of if you have a similar laptop, that's the type of performance you can expect. If you only use the CPU, you might get half as that. You can try it later. On my RTX 2060 Super on my desktop, which has a CPU of a 12-core, 24-thread CPU. It's a Xeon 2678V3. I can get 3 to 4 times the performance you see there, even though the RTX is above 3 to 4 times powerful than this laptop's GPU. So that means the bottleneck is also the CPU and also the PCIe bandwidth between the CPU and the GPU. So before going out there and buying a big GPU, make sure the other companies are followed. So later in the video, we're going to profile and show and talk about bottlenecks and some suggestion for hardware. You can see that we have 8 environments running in parallel. That's because we train it on 8 environments in parallel, and usually it takes a number of threads of your CPU by default to specify the number of environments. So if you just want to train on one environment for some reason because you're training or you're doing some other task in parallel, you can do that. You just use the num-env argument. So since it only trained for 10,000 steps, time steps, it's it doesn't go very far. So just for fun, let's try only on the CPU. So the way to disable the GPU, one way to do it is to use this. So you use the CUDA visible device variable and set it to nothing. Let's try. So normally you should not use the GPU at all. It should stay at 0. So yeah, we get about half the training performance. Now, if you don't have a GPU and you have a similar CPU as my laptop, this is what you can expect, which is not bad. You can still train on some simple games. In order to improve performance, you can, because one thing, this TensorBoard package is not necessarily optimized for this CPU's instruction set. So you can have a custom build TensorBoard package for your CPU. That could help also. And then play also with the number of environments. In order to integrate the game Hang-On, we first need to cover some reinforcement learning concepts. So reinforcement learning is about training your model through rewards as opposed to explicitly coding the rules, like for example, using state machines or behavior trees to explicitly design and code which target the gun aims at, or if it needs to get ammo or health packs, for example. This works for simple games such as this one. This is a Terminator 2 arcade for Sega Genesis, if you want to know. But for more complex ones like Dota or Go, it's practically impossible to do that. So this is why you need a system like RL, where you instead let the model figure out the solution by just giving it a positive or negative reward for each of its decisions. So the most critical component of reinforcement learning is the reward function. You can see at the top left of the screen, the green spikes. At every time steps, the reward function returns a reward based on the environment. In this case, you gain points by shooting an enemy and it returns a positive reward. If you get hit and lose health, it returns a negative reward. So this is the down spikes, as you can see right now. Otherwise, it returns 0. It's pretty simple, but it gets the job done for this game. Next important component is the model. You can see below the reward function. There can be many types of models. We'll see more details about them later in the video. In this case, we have 1.7 million parameter convolutional neural network, which are typically good for image recognition. The model is the brains of the system. It takes the state of the game as input and outputs an action. You can see it like that. So this model takes a stack of the last 4 frames as input. So as you may have noticed, the frames are downsampled to 84 by 84 and to grayscale. So the reason is that for neural nets inputs, you need to aim for the minimum amount of data. So in other words, the more unnecessary details you feed the neural net, the longer it will take to get to an optimal solution. And this is found out by experimenting. So in this case, they found, if you see various research papers, often they use this size, and it was found out by experimenting, which amount of details is really necessary. Next, you have the filters, like the 8x8, 4x4, and 3x3. This is what characterizes a CNN. Their purpose is to extract several levels of features from the image and feed that into the fully connected layer. So in this case, 512 units. This layer is where the classification of the different game situations are encoded. Finally, you have the output layer. So the 126 different button combinations from the Sega Genesis gamepad. The model outputs a probability for each of the actions. The probability represents the confidence level for having a reward. So for example, if button A has the highest probability, that means the model thinks shooting has the highest chance of returning a reward in this situation. The third important component for RL is the algorithm and training process. In this case, we use the PPO algorithm, which was used for OpenAI databots, but we won't go into details in this video, but rather talk about the general training process. As you can see below the model, there is the CPU and GPU usage. So you may notice the GPU spikes. This is when the training of the model happens. That is when it gets its parameters updated. After the model plays another batch of game sessions to collect experience with its newly updated parameters. So it continues to do that in a loop until the target time steps are met. So if you remember, the time steps are specified in the command arguments from the example earlier. So how the model updates its parameters? There's many ways to update model parameters. One of them is called backpropagation, but that's the subject of an entire other video. But the main point is that every solution at the end tries to update the model parameters in such a way that next time the model meets the same game state, it will output a higher probability for the action that gives a positive reward, or reduced probability for the action that gave a negative reward for that specific game state. So if you repeat this process long enough, over millions of time steps, depending on the game, and the reward function is good, the model should converge to an optimal solution. So you might think this is a very slow process and takes much more time than a human, and you're right. This is a problem for our solutions currently. They are not simple efficient. So there is potential solution for that, such as imitation learning. If maybe you have heard about that accelerate training by looking at human examples. But we won't cover this in the video. Another important point is that how you code the reward function. Another important point is that how you code the reward function can have a big impact on the behavior. So in this case, you just saw a boss fight, and this boss fight has a big problem. Is that probably it's a bug in the code, but when you hit one of the parts of this boss, it doesn't return a reward. So at first I didn't realize that, so I was wondering why after over 1 billion frames of time of training, it didn't converge to beat the boss. And then when I debugged it, I found out that one of the components of this boss didn't return a reward when hit. So in other words, the reward was too far away. That means at the end of the boss fight, for the model to be able to figure out what to do. So another example of how the reward function can drastically alter the behavior of the model is with Super Mario Bros. 3. So in the original OpenAI integration, like in the Retro repo, the reward function is as follows. It only uses the score. So every time you have a higher score, you gain a reward, and that's it. And when you run a model for it, like I ran it previously, you get this result. So you see it comes back. Since in Mario 3 you can come back, it can easily farm, and the enemy responds, it can easily farm rewards. And actually it's the correct behavior, because according to the reward function, it does the maximum to get rewards, and this is the correct behavior. But when we play as humans, we have some sort of intrinsic rewards where we want to explore and move forward and beat the levels. So I can show you an example of how we can change that reward function so that it moves forward. So I'm gonna load. So this is what I edited previously, and I put it in my fork of Retro. You can find on my GitHub. So I added the position variable. So this is read from RAM. And when you see in the scenario with the reward function, I added this to the reward. So I kept the score, but also added the position. So every time Mario advances, this variable increases, and also when it gains lives. So using this, I read another training session, and I got this result. I made a GIF out of it. I'll put down below a link to the whole process I used to make that, but I don't want to make this video too long because it's more about the game Hang On. Another important point I want to talk about is long-term rewards. So right now what's running is Super Mario 2, the Japanese version. This is the version that was too hard for the American market. So the Super Mario 2 for America was different because this one was the Japanese version was too hard. And it's quite funny because for AI it's also too hard for different reasons. I don't know if it's very clear, but there's a certain point where the AI has a lot of trouble and jumps in the hole. So more specifically, this hole. So one of the key challenges with reinforcement learning is to know which action was critical in getting the positive or negative reward. So in this case, when Mario jumps into the hole, it obviously gets a negative reward. But the actual critical decision that got us there, that got the model there, is that he is here, like he didn't jump on top. But both paths leads to positive reward until he gets into the hole. So he has a lot of trouble associating this decision to the negative reward, which is too far down the road. For a human, it's really short, but for the way the reinforcement learning algorithm works, in this case, it's quite long. So you can easily imagine for RPGs like Zelda, where you can get an item that will be useful like 1 million time steps later. It's almost impossible. You need to have other techniques. You need to you can use imitation learning for that and have some form of curriculum. There's a lot of technique you can use, but certainly not this process. So next step, we're gonna set up the integration tool. So first we need to install some dependencies. So Captain Proto, Cap PNP. And then the Qt libs, this is for the interface. The OpenGL part because it needs to render the game inside the editor, the integration tool. It's already installed, but you can just press enter and it will install it straightforward. So once this is installed, you need to build the makefile. So you can invoke a cmake. So debug build on. And this is enough to build the makefile. Should be quite fast. I think it needs to download some dependencies, but usually it's quite fast, depending on your connection. And once this is done, you just run the makefile. You can run like this, but if you want to use all your cores, a trick you can use. So you grep into your number of processors. Get the CPU info. So that should be okay, and then it's gonna compile pretty fast, a few minutes depending on your CPU. So once that, you should be ready to run your the integration tool. So it's called GIM Retro Integration, like this. So it works. You can open a game to see if it works completely. So let's open Super Mario Bros. 3. So it works. So now we're ready to integrate the Sega Genesis, the Sega Master System game Hang On. So first I suggest you copy it from another existing Sega Master System game and rename the folder Hang On -SMS. So I already done the integration, and I put the final solution on my GitHub in the Retro mods, which is a fork of Retro. You can find it there if you have trouble. So first, before opening the integration tool, this game with the integration tool, I'm going to go through the basic files. So data.json, this is where all the RAM addresses are defined. And these are used for the reward function. So for example, if you need the score to make your reward function, you need to know its address in RAM, so that the Retro can extract it from the emulation. Now, to find these values, there's two main ways. First, is to find it yourself. I'm gonna with the integration tool, you can do that. Or if you're lucky, someone already has the mapping, put the mapping online. Like there's a site called, I think, Data Crystal, that has many NES and Sega ROMs, Sega Master System ROMs that already dump. But in my case, Hang On was not there, at least at that time. So I found these values myself. Metadata, in our case, you just put the default state. So a state is, like, for example, a start state, because when the model plays the game, you don't want it to start in the menu, because you don't want to train on the menu. You want to start at the actual beginning of the game. So you have to save that state, so that Retro can knows where to start in the game. This file is for the checksum. So how to find this checksum? You can use the import tool to find this checksum. So you just run like I showed you before, the import tool on that ROM, and it's gonna show you the checksum, and then you put this you put it in this file. The import tool will copy the ROM directly there after you got the right checksum. Scenario.json is basically it's your reward function. So in this case, we just use the score, and in this case, Hang On, the score is enough, because every time the moto advance, you get a bigger score. And this is a done condition. So Retro needs a way to know when the session stops, because let's say you die or you win the game, there's no way to know that you won the game except through this, where you specify where you have to specify whether the series of conditions are necessary for the game to consider being done. So in case of Hang On, there's quite a few. There's just 3 of them. Is the time needs to be 0, but also the speed needs to be 0, because there's some parts of the game where the time is 0, but it's just because it's the end of of a level, and you can continue to the second to the next level. So the speed needs to be 0 for that. And got another component is crop. So we don't crop this game because it's not necessary, but some games you want to make it easier for the model. You want to crop part of the UI. And that's it. So you can have, I forgot to mention, you can have more than one state. So for example, Super Mario, not this one, the first one. Hold on. Like, okay, for example, this one. You want to have, for example, you want to have many start states for many different levels. Then you have to register. You have to save many different states. So now we're gonna open this ROM. So how to open it? You just double click on the ROM. That's it. Then if you want to load a state, like the start state, you get it here. So you see there we have all our variables read in RAM. So the score is at 0 because we didn't have move forward yet. The speed 0 because we're not moving. And the left is the distance left, and time is the current, obviously the current time. So just to show you that it works, so you see it's moving forward, and the speed is 115, and the score is increasing. And it's too fast to see, but you see that the reward is getting positive every time it moves, because the score increases, then the reward gives you. So this is how you can debug the reward. So you see in our case it works, it gives a positive reward. And then the done here is the done condition. Of course it's no because the game is in progress, but if you die it's gonna turn yes. So let's say we let the timer run out. So you see it turns yes. So with the iteration tool you can debug this. So first step, you might want to know how do you find these values. So first thing is we need to find the RAM values, the RAM addresses of these variables. So in order to do that, we can use the search tool. And so first you need to give a name. So we're gonna give it score 2 because we already have score. And now we need to assume something. So typically the score starts at 0. It's not always the case, but typically it starts at 0. So you can use the is operator and then 0 to search all the values that are currently at 0. So as you can see, there's a lot, but it's a start. So now the goal is to narrow down this list. And one way we can do that is play the game and move forward and see which one of these values increases. And we can do that by using the increase operator and performing a search. So we're gonna move forward, search, narrow down the list, move a bit, search again, search again, then repeat this process. So now we're pretty close. We have 31 items. And you see the score is 1,170. And there's some values definitely that are close to that. So if you look at these values, it's pretty clear which one is it. So it's this one. So once you found out this one, and then you can do make variable. So once you found out the RAM address, you need to find out the type. So the type is to find the right type. It's a trial and error process. If you want to have information on that, in the game interrogation doc from OpenAI, describes all the different types you have, like the sign, unsigned, binary coded, decimal, loanable, binary coded, decimal, and then the endianness, little and big endian, and give some examples here. So to find this type is sometimes it's quite long, and also depending on what type of variable you want to find, it can be quite tricky, because sometimes they, especially for retro games, they use a lot of optimization to pack the to take less space, or they had some other issues which ends up having obfuscated variables, so obfuscated values. So sometimes it's quite tricky, but with using these operators, you can find most of it. So for the rest of the variables is the same principle. So then once you have your variables, you can edit your scenario. So in here we have a simple reward function. So at the top, this is where you specify the reward function. So let's say you want to add another score 2. So we can just put add reward. And then you can, here the delta means that changes in the score will give you a reward, because you don't want, in case of the score, you don't want to give a reward every frame because he has a positive score. The game has a positive score. You just want to give a reward when actually the score increased, so you use delta. And then you also sorts of conditions if you want. You can give a penalty to, depending on what variable you have, you can give a penalty if you want. And with one of these operators, we're going to remove it. And then here it's the done condition. It's more complicated than the reward function in this case. So you add the done condition here, and then we don't want delta because we want the absolute values. And the time is 0, like we explained before. Left is not 0, so like the distance left is not 0, and then the speed also is 0. So because if there's some cases where, like I explained, where you just actually cross to the next level, and the time will be 0, but actually the game continues, so you don't want that. So that's why you need to check the speed. So once you specify that, you click save, and it should save the JSON file. Also, you need to save a state. So so basically, you play yourself to the point of the game where you want the train to start, and then you save that state, and the retro will load from that state every time. There's other functions here, like episode record mode and record movie, but we won't go to this in this video. It's not necessary to get the model working. So now in theory, we're gonna delete this. So now in theory, we're ready to start training our model on Hang On. Before we start training, you need to add the Hang On game in the list. So with Visual Studio Code, you can open the baseline folder that you clone, and go into the run file, and then you add it to this list. So every time you integrate a new game, you need to add it to this list. This is some bugs that they have, and that was still not fixed. So you need to do it. It's annoying, but otherwise it will complain that it doesn't find the environment. I strongly recommend that you log everything by default, and especially metrics to Tensorboard, for Tensorboard. So the way to do that is to set some variables. So this one is OpenAI log format, and this is where we're going to set we want all the prints in Tensorboard metrics. So this way. And the other variable that we need to set is the log directory. So in our case, we're gonna put it in our home directory and the Hang On logs subfolder. So now we're ready to type the command and issue it. So it's basically very similar to the example we saw at the beginning of the video. Except that we're going to use the Hang On environment. We're gonna the first test, we're gonna run it for 2 million frames. That should be enough to have good results, at least for the first few for the first minute of the game. And also, this is a new argument, is a safe path. So what this does is going to save the model of your training. This is pretty much important, because otherwise, the next time you want to continue the training, you're going to have to restart from scratch. So be sure to save your model so you can load this model back next time you want to continue the training. I'll show you how. So now you're ready to start. I already run that before, because it takes about 2 hours. So once you have your model, what you can do if you want to play it back, you can instead use load path, and you also use load path when you want to start your training from a specific model. And on time steps you put it to 0. So and then the play argument. So what this does is that it's not going to train, but it's still going to load the model and then play back that model. Let's see how it goes. Oh, I'm in the wrong directory. Sorry. Here you go. You can see the results, not bad. They can make turns. But it seems it doesn't know how to keep up its speed, so it runs out of time before reaching the end. So if you train this for 500 million frames, you're gonna beat out the whole first level of difficulty easily. So as you can see that on this type of hardware, on the laptop hardware, it could take around maybe 2 weeks of training to get to that, to beat the game. So once the training is done, you should CD to your log folder, which is hang on logs in our case, and then the TB subfolder, which stands for Tensorboard. So to launch Tensorboard, just type the Tensorboard command, log the argument, and then you select the current directory. This is where your events file are. So we'll give you a link. So basically you view the data in your browser. It's pretty convenient. By default, Baseline doesn't log many metrics, but enough to be useful. So for example, we got the most important one, which is a reward graph. So we trained for 2 million time frames, 2 million time steps. So it's 2K times 1000. And you can see it's progressing rather nicely. You have other metrics such as the FPS. So let's say you run this on a server, a remote server, and you wonder why it takes a long time. And you can see if there were some performance problems along the way, like another process running or something like that. And this is the length of the episodes, so it's pretty consistent with the reward mean. So normally you should have much more data than this, but you would need to add it yourself in the baseline code. I think stable baseline and fork of baseline have more metrics. I tend to do another video about stable baseline because it's a much cleaner code actually, but it's a bit harder to use for a retro game at first. But if you want to do customized solution, it's the way to go. And they log more metrics. So you can take a look at that and import it back in baselines if you want to continue using the original baseline repo. Next, we're going to take a look at the models. So you can find the models in the comment folder. So So you have, as you can see, you have several models, and it's easy to add your own one. You just need to register it and define it. Most of the CNN use the one defined in the, I think it's DeepMind's original Nature paper. Here you can recognize the filters I showed you previously with the Terminator and Hang On example. So the 8x8, 4x4, 3x3 example, and then they add they connect to the fully connected layer of 512 units. A model I haven't talked about yet is the multi-layer perceptron, the MLP. So this model is much simpler than the CNN, but it's mostly used for physics examples, like the walking biped or spiders example, the ones that learn to walk. So for things like that, so examples that are not image based. That said, you can still try it on image based games, and I tried it on Hang On and Super Mario, and it's quite funny because for the first few minutes of the game, for the first parts of the game, it actually works quite well, and even better than the small version of the CNN small here. But eventually you see that he has trouble generalizing because it's not structured for extracting features and images. So in the short term, you might think that it's has better performance, and also the training FPS is better because it's a more lightweight model. But eventually, you're gonna see you're gonna have lots of trouble generalizing. But you can still try it. It's quite funny. And I'm gonna show you a video of an MLP versus a CNN with Mario in a couple of minutes. So this one, like I just said, the CNN small version, it's just a smaller version of the default CNN model, only 128 units. I tried it on Hang On, and it has trouble. It converts to an optimal solution much more slowly, and after 500 million frames, I think it just managed to get that 2/3 of the way of the game. So again, this is a more lightweight model, so you're gonna have a better training FPS, but eventually you pay for it by a lack of performance. In terms of learning. One thing you can try is that you can slowly add a filter or increment the fully connected layer. See exactly at what point where it becomes a better learner. That's one thing you can try. Next is the LSTM. So this is the long short-term memory network, and then combined to a CNN. This actually, the main point to understand with this is that the CNN alone is state independent. That means for a given image, which means a given game state, is going to treat it independently no matter what happened before. So basically, for example, if you're near an enemy and you know that enemy, I don't know, like a minute ago got a very powerful weapon, your reaction should be much different than if that enemy doesn't have any weapon, like, or got a much weaker weapon. And let's say in the game state you don't see which weapon the enemy is hiding. Well, the CNN won't see that. Like, he will treat exactly the same no matter what happened before. Meanwhile, the LSTM model, it says in the name, it has memory. It's gonna consider the sequence of events that happened before. So for certain games, you're gonna have a higher performance in terms of learning. That said, it's more heavyweight, and and for simple games, you might not really see the benefits, but you can still experiment with it. It's worth for the learning experience. Got other types of networks, like just the filters without the fully connected layer. And Impala, I didn't check it. I know about the paper, but I didn't check it. I didn't try it. And also it doesn't fit in the in under 2 GB of VRAM. So I want to try it on eventually on my RTX. Maybe I'll make a video about it. So this is a video I made previously. You can see on my YouTube channel. So on the left is the MLP model, and on the right is the CNN model. So you see the performance is similar. And you see the MLP model found the secret pipe, most likely by luck. And actually wins the race against the CNN, which is incredible because it's not made for image-based situations. But eventually you're gonna see that in the next level you're gonna have a bit of trouble with some parts with the beginning of the level. So you see he has trouble like going over these obstacles. And then you can check the CNN one, how it's going to react to the same situation. And much better. So it jumps over it. And went under faster instead of trying to jump. So you see now it's much better. Even though it died to a plant, it's much better. So you can already see that the MLP model will have lots of trouble going forward. Meanwhile, we're in the code. We can check the retro wrappers. This is where it converts the original input image from the consoles, like the Sega Genesis, and convert it to 84 by 84 with a stack of 4 frames. So if you go to retro wrappers in the common folder, wrap DeepMind retro function, you can see what transformation it applies. So warp frame is it's a downsample, so 84 by 84. Clip reward is like the eclipse. Well, it says what it does is it clips the reward of the environment, because sometimes if their environment returns exaggerated rewards, it can skew the learning. So it's important to have to keep it within bounds. And this is a frame stack, the stack of 4 frames, and it scales the pixel value between the 0 and 1 to 0 and 1. So we can good learning experience is that you can try to change some of it and see how it affects the training process, like removing the frame stack. See what happens. Certain games the performance is going to be the same, and the FPS is going to be higher because the model is going to be lighter. But for other games, without having the velocity encoded, the direction of the object encoded, it might cause problem. You can also, if you have a game that you suspect doesn't have enough detail because there's a lot of details in the image, you can change the size of downsamples to inside this function. This is there's a time limit for so let's say you didn't code your done function properly. There's still a time limit, but I wouldn't count on that. And like for example for Terminator, the time limit is pretty high. So for Terminator 2, eventually ends, but the boss fight I was talking about that didn't return a proper reward, so the game was in an infinite loop, basically. If that's your case, you should definitely check that. Then the stochastic frame skip. So this sort of skips a frame randomly, and apparently the result is that the learning is more robust with that. So it adds a bit of randomness in the action. What I mean skip a frame is this is the action you take. It's going to be repeat for 4 frames, but sometimes you can skip the repeat of this action. So apparently this randomness adds some robustness into the learning. Again, you can experiment with and see for yourself. Another question you might have is how to save videos. There's quite an easy way is to add these arguments. So save video interval 1 and save video length, and you can set it to the same number of time steps or lower. Press enter. So you're gonna notice that the training is a little bit slower. Maybe you lose 70 FPS. And this video is gonna end up in your logs folder that you specified with the shell variable right here. Just gonna wait for the training to be over. Should take 1 minute. In the meantime, just for fun, we can check the CPU usage. So you can see that it launched a process for each of the environments. And technically you could run 2 training in parallel. You would have lower performance, but still higher than just one at a time. So it's done. You can check the video. So since it's just trained for 20,000 frames or so, it doesn't go very far, but you get the idea. It renders all the environments in a video, and it's quite useful for debugging. Now you might ask how to make videos that I showed you with the Terminator and Heron example. I coded this interface myself, but the code is quite hacky and unclean and very hard coded. But if enough people want it, I can work on it and put it on my GitHub. I hope you have found my video useful. If there's some topics you want me to expand on, because in the video I cover a lot of concept and I skip over some details, I feel, please don't hesitate to let me know in the comment section down below. Also, if there's some games like I did for England that you want me to integrate that's not in OpenAI's list of already integrated game, please tell me. But except RPGs probably, because kind of hard, but we can still try. So thanks for watching, and don't forget to press the like button.